Welcome, everyone. Ready to dive deep into control systems?
Oh, yeah. Control systems, they're everywhere.
Everywhere. Really? I mean, like where?
Well, they're like all over. You got your thermostat at home.
Right.
And then there's like self-driving cars, all that.
Okay. Getting it. So they're important, I guess.
For sure. Super important. But a lot of folks, they don't even realize.
Yeah, I kind of get that. So, like, back up a sec. What is a control system exactly? Like, explain it to me like I'm 5.
Okay. Imagine like a system, any system really.
Okay.
Could be a car or a robot, even something simple like a coffee maker.
Right.
The control system, it's like the thing that makes that system behave the way we want. Like a conductor for an orchestra.
Gotcha.
Yeah.
A conductor, making sure the music's right.
Yeah, exactly. So just like an orchestra has its instruments, the control system, it's got these key parts. First, there's the plant, which is, well, the thing being controlled.
The plant. Sounds kind of weird for, like, a car engine.
Right, it's just a technical term. It could be an engine, a chemical reactor, really anything.
So the plant is like the star of the show.
Exactly.
Yeah.
Now, every star needs direction, right?
True.
That's where the input comes in. It's like giving instructions or commands to the plant, like in your car when you hit the gas or turn the wheel.
So the input's the director telling the actors what to do.
Perfect. And then the plant, following those instructions, it does something, right? It produces an output.
Like the car moving or changing direction.
You got it. It's all cause and effect. Input, plant, output.
But where's the actual control part happening? This is where it gets kind of mind-blowing, right?
Totally. Now, the controller steps in. It's the brains of the operation. It's constantly comparing what's actually happening, what we want to happen, and then it makes adjustments to get things just right.
So if I'm cruising at, say, 60, the controller is like my co-pilot keeping me there.
Exactly. Uphill, downhill, wind, whatever, it adjusts to keep you steady.
Wow. Like an invisible hand, making sure everything's right.
You got it. But it's not magic, of course. It needs information to make those decisions.
Oh, right. Information. So, like, is it reading my mind or something?
Not quite mind reading. That's where sensors come in. They're like the eyes and ears of the whole system.
Okay, sensors.
They're measuring everything, speed, temperature, whatever's important, and feeding that back to the controller.
Got it. Sensors for info, controller for decisions.
Now you're getting it.
But how does the controller actually do stuff with that information?
Well, it tells the actuators what to do. They're the muscles, the ones actually making things happen.
So it's like a chain reaction.
Yes. Input to the plant, sensors measure, controller decides, actuators do the work.
Wow, crazy how it all works together.
Right. And this is just the basics.
Wait, there's more? Different types of control systems?
You bet. Different systems for different jobs. That's where things get really interesting. All right, so let's start with open loop control. Pretty simple stuff, actually.
Okay, simple. I like it. Less for my brain to process. Break it down for me.
Basically, you got actions that are like pre-programmed, no feedback involved. Think of a timer on a sprinkler system.
Oh, yeah, those things. Set it and forget it. But what if it rains?
That's the thing. It doesn't care. Rain or shine, those sprinklers are going on.
So open loop is a bit inflexible, huh?
Yeah, exactly. Works fine for predictable stuff, but not so much when things change unexpectedly.
Makes sense. So what do you do when you need to adapt, like on the fly?
Then you bring in the big guns. Closed loop control. This is where feedback comes in.
Feedback, like we were talking about before.
Exactly. It's constantly checking, are we where we want to be, and then making adjustments if we're not.
Okay, so closed loop. It's like always paying attention and making corrections.
Think of your car's cruise control. You set the speed, and the system does the rest, even if you hit a hill.
It keeps you at the right speed. I get it.
Right. That's closed loop, keeping things stable even when things around you change.
Gotcha. So the controller's still the brain, but now it's got this feedback loop helping it make smarter decisions.
Precisely. It's not just reacting, it's like actively keeping things in check.
So how does it actually figure out what to do? Does it have like a cheat sheet or something?
Not exactly a cheat sheet, but it does have a control strategy. That's the algorithm, the rules it follows.
The rules of the game.
Right. And there are tons of different strategies out there, some super complex.
So it's like the controller has different plays for different situations.
Exactly. One of the most popular ones is the PID controller.
PID. Sounds kind of technical.
It stands for proportional integral derivative. It's basically 3 actions combined to handle the error signal.
Error signal. Remind me what that was again.
It's the difference between what we want and what's actually happening.
Right, how far off track we are.
Exactly. So the proportional part, it reacts directly to the current error. Bigger error, stronger response.
So if I'm way off course, it's like a hard yank back on track.
You got it. Now, the integral part, that's more about the long game. It tracks accumulated error over time.
Ah, so it's learning from past mistakes.
You could say that.
Yeah.
It helps eliminate any persistent error, make sure we hit the target precisely.
So even tiny errors, it's like, nope, gotta fix that.
Exactly. And then there's the derivative part, which is all about anticipation. It sees how fast the error is changing.
Oh, interesting.
And uses that to prevent big swings or overcorrections.
Like it's predicting the future.
Kinda. It helps keep things smooth and stable.
So this PID thing, it's like the whole package, huh?
Yeah, it's a classic for a reason.
But you said it's used in the real world, not just theory.
Oh, absolutely. PID controllers are everywhere. Industrial processes, robots, even your home thermostat, probably.
Wow, no way. I never realized.
They're the workhorses of the control systems world. But of course, for really complex stuff, we need even more powerful tools.
More powerful, like what?
Think about those self-driving cars we talked about.
Oh yeah, those are mind-blowing.
PID wouldn't cut it for something that complex. That's where something like model predictive control comes in.
Model predictive control? That's a mouthful.
We usually just call MPC. It's a whole different beast, much more strategic.
Okay, I'm intrigued. Tell me more. All right, lay it on me. What's this MPC all about?
So MPC, it's all about thinking ahead, Like, it uses a model of the system to predict what's going to happen in the future.
A model, like a miniature version.
Not a physical model, more like a mathematical one.
Equations and stuff.
Exactly. It uses those equations to kind of simulate what the system will do.
So it's like looking into a crystal ball to see the future.
Yeah, kind of like that. And then, based on those predictions, MPC figures out the best way to control things.
The best way? There's like a perfect way to do it.
Well, the most optimal way, considering all the limitations and stuff.
Okay, it's starting to get a little fuzzy here. Maybe an example would help.
Sure. Remember those self-driving cars we were talking about?
Yeah, perfect example. How does MPC work there?
So, imagine the car is going down the road.
Okay.
It's got all those sensors feeding information to the controller.
Right. Cameras, radar, all that.
Now, MPC uses that info to predict, like, okay, if I keep going straight, I'm going to hit that pedestrian.
Uh-oh, that's not good.
Right. So it starts calculating, what if I brake? What if I swerve? What's the safest, smoothest way to avoid this?
So it's like playing out all the different scenarios in its head.
Exactly. And then it picks the best option and sends the commands to the steering wheel, brakes, and all that.
Wow. So it's not just reacting, it's actually planning its moves.
That's the beauty of MPC. It's like chess, Always thinking several steps ahead.
I'm starting to get it. So MPC for the complex stuff, PID for the more basic stuff.
Yeah, you could say that. PID is great for, like, keeping a temperature stable.
Okay.
But MPC is what you need for those really intricate, dynamic situations.
Like navigating a busy street with pedestrians, other cars, all that chaos.
Exactly. It's used in all sorts of fields, actually. Robotics, finance, even energy management. Anywhere you need to optimize something complex, MPC is your go-to.
Man, control systems are way more powerful than I ever imagined. And to think they're working all around us all the time.
Right. It's kind of mind-blowing when you think about it. And it's only going to get crazier in the future, with AI and all that.
Yeah, the future's looking pretty automated. Makes you wonder where it's all headed, right?
For sure. I mean, think about it. We're already trusting these systems with driving our cars, managing our homes, even performing surgeries.
It's a lot of responsibility for, well, a bunch of algorithms and sensors.
Exactly. It's up to us, the engineers, the scientists, everyone, to make sure these systems are developed and used responsibly. We got to remember they're tools, powerful tools.
Yeah.
And it's up to us to use them for good.
That's a great point. Food for thought, for sure. Well, I think that about wraps up our deep dive into the world of control systems.
Yeah, we covered a lot of ground today.
From the basics to self-driving cars, MPC, all that. My brain's kind of fried, but in a good way.
Me too. It's always fun to explore this stuff.
Thanks for taking us on this journey. Until next time, everyone, keep those brains buzzing.